Hello. In this video, I will explain how I generate Mandelbrot fractals. Mandelbrot found that by using a simple algorithm on complex numbers, he could generate interesting patterns. Since it all hinges on complex numbers, let's talk a bit about them first. You know that the square root of 9 is 3, or negative 3, but what is the square root of negative 9? The square root of a negative number cannot be real, so we call them imaginary numbers. If we factor the square root of negative 9, we can write it as 3 times the square root of negative 1. Any imaginary number can be written as the product of a real number and the square root of negative 1. To simplify the notation, we write the square root of negative 1 as lowercase I. If a number has a real component and an imaginary component, we call it a complex number. We write it as z is equal to a plus bi, where a and b are real numbers. We'll need to graph complex numbers. To graph two-dimensional real numbers, we use the Cartesian coordinate system. We had the x-axis and the y-axis. We can graph complex numbers in a similar fashion using the imaginary axis and the real axis. Here's an example. The real part of z is 2 and the imaginary part is 3i. So we plot it as shown, which is very much like how we plot the real numbers on the Cartesian coordinate system. Squaring complex numbers produces unexpected results because I squared is equal to negative 1. Mandelbrot examined what happened to complex numbers when subjected to a simple squaring algorithm. Let's see that algorithm. First, we choose any complex number c, then start an iteration by setting z0 equal to 0. Then z1 is equal to z0 squared plus that number c. Then z2 is equal to z1 squared plus c. Then z3 is equal to z2 squared plus c. In other words, for any z in the sequence, it's the sum of the previous z squared plus c. Depending on the value of c, the algorithm or iteration will either diverge, shoot off to infinity, or not. For example, here c is equal to 1. There's no imaginary part. We set z0 equal to 0. z1 is equal to z0 squared plus c, which is just 1. z2 is equal to 1 squared plus 1, which is equal to 2. z3 is equal to 2 squared plus 1, which is equal to 5. z4 is equal to 5 squared plus 1, which is 26. z5 is equal to 26 squared plus 1, which is 677. Obviously, this sequence will diverge. Here's a similar example. This time c is equal to negative 1. Again, there's no imaginary part. We set to z0 equal to 0. z1 is equal to 0 squared plus c, which is negative 1. z2 is equal to negative 1 squared plus negative 1, which is equal to 0. z3 is equal to 0 squared plus negative 1, which is equal to negative 1. z4 is equal to negative 1 squared plus negative 1, which is equal to 0. z5 is equal to 0 squared minus 1, which is negative 1. This sequence oscillates between 0 and negative 1, so it does not diverge. One final example. This time c is equal to I, and there's no real part. So z0 is 0, z1 is 0 squared plus c, which is just I. z2 is equal to I squared plus I, which is negative 1 plus I. You'll notice that by definition, I is the square root of negative 1, so I squared is equal to negative 1. z3 is equal to negative 1 plus I all squared plus I. which expands to 1 minus 2i plus I squared plus I. Replacing I squared with negative 1, we get 1 minus 2i minus 1 plus I, which gives us negative I. Continuing, Z4 is equal to negative I squared plus I. And since negative I squared is just equal to negative I times negative I, which is plus I times plus I, which is just equal to I squared. So Z4 is equal to negative 1 plus I. Z4 is equal to Z2, so this sequence will repeat itself and oscillate between negative I and negative 1 plus I. Therefore, it will not diverge. Mandelbrot was interested in all points C that did not diverge. This set is called the Mandelbrot set. We denote it by M. It is not necessary to examine every complex number C. We need only to examine the following subset. Here's the part we're interested in. The real part goes from negative 2 to plus 0.5, and the imaginary part goes from minus 1 to plus 1. So we subject every point in this area to the algorithm, and if it does not diverge, we say it belongs to M, the Mandelbrot set. If a point does not diverge, we color it black. Otherwise, we color it according to how many iterations were required before it began diverging. And here's the result. The Mandelbrot set consists of all the points that are black. When we zoom in on this image, we find that the shapes are replicated. Watch the following short video. Notice that the cardioid shape repeats as we zoom in. There it is there, coming right back to us. And again as we zoom in even further, etc. We saw only red points around M. When we zoom in much further, many more interesting colors and patterns appear. So, here's how we zoom in. Divide our area into 1,600 columns by 900 rows. This gives us 1,440,000 points. Choose any point to zoom in on. This is our target point. Perform the algorithm on every point in Z in that area and color it appropriately. This will give us the first image we save as picture 1. Now we make our area of interest smaller, but still make sure it includes the target point C. Divide this new area into 1,600 columns by 900 rows and do the algorithm for every one of the points that you have. We saved the resulting image as picture 2. Now repeat this process thousands of times, and we'll end up with thousands of pictures that we use to make a video. In the process, we'll get some interesting pictures. Like this one, for example. Different target points generally produce different videos or different images. Gradually, the area we're examining gets very small, and when we divide it into 1,440,000 points, the distance between these points is very small. Even using double precision arithmetic, we will still encounter many round-off errors. To fix this, I wrote a library of high-precision arithmetic functions. I can compute to whatever precision I want, but I generally stop when dealing with numbers smaller than 10 to the minus 40. Finally, I should mention that I use C# in Visual Studio for my programming, and to speed things up I use the graphics processing unit for my calculations. The GPU is much better at parallel processing. And that's about it. If you have any questions, feel free to contact me.